Hello. We are wrapping up this unit. We are at the end of this unit. We are talking about our very last pieces of information that we need to know in order to fully understand normal distribution. So what we've talked about so far is we've talked about how to calculate uh, percentages or probabilities given a certain value, right? We're like, okay, what's the probability that we have picked this? What's the probability that we picked greater than or equal to this? So we're talking about like, okay, we've been given a value with our normal distributions, with our normal distributions. We have a given value and we're told find the probability. Or sometimes we say percentage, which we know we would just then multiply by 100. We now are going to talk about a second type of normal distribution problem, which honestly is probably the most common one because it's the one that makes the most amount of sense when we're trying to analyze this in the real world. The inverse normal distribution is exactly what you know about inverse functions. So remembering all the way back to when we talked about inverse functions. And inverse normal distribution is when we take our input and our output and we switch them. Okay, so we're normally given a value and told to find the probability and percentage. Now it's just going to be flipped. We're going to be given probability, more often given percentage. Find the value. So the reason why we would ask these types of questions is more like, okay, given a normally distributed situation where the mean is this and the standard deviation is this, what is the top 10%? What is the bottom 10%? If we know that above a certain number is classified then as oversized, or maybe a certain number is classified as gifted and talented student, right? Your MAP testing, if you remember all the way back to when you used to be taking your standardized MAP testing online, they gave you a percentile. And that percentile meant that like you were in the top, if you were maybe a percentile of 80, you're in the top 80% of all of the people in the world. So normally we're given a percentage and told to find what is that value? What does that value mean? So let's go ahead and practice it. Example number 3 of our notes. Since November 2007, the average time it takes for fast trains, like Eurostar, to travel between London and Paris is 2 hours and 15 minutes with a standard deviation of 4 minutes. And we're going to assume a normal distribution. So we need that in order to then calculate with normal distribution. If we're not told that it's normal, then we can't use those calculations. And sometimes you might be given probability problems where you start out the problem just calculating probability like you normally would without knowing anything about normal distribution, like how we learned all the way back to our other probability unit. You would just be like, you go into a problem and you're like, oh, it's like this type of probability, boom, 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 boom. And then at some point they're like, hey, by the way, this is normally distributed. Now find this. And then you have to like switch gears of how you found the probability and use normal distribution. So don't ever assume normal distribution. If it doesn't tell you that it's normally distributed, then you have to do your other probability type of processes. Okay. What is the probability that a randomly chosen trip will take longer than 2 hours and 20 minutes? So we want a probability and we're given a value, which means we're just doing our normal distribution. We're going forward the way we normally do. This would be your normal CDF. So if we pull up normal CDF in our calculator, we're asked to find the lower bound. Longer than 2 hours and 20 minutes means that we want to be at that or above. And so what we would put here is kind of hard with hours and minutes because the 1 hour is actually 60 minutes. So a lot of people would want to do this as like 2.2 hours, which is incorrect. So whenever I'm given like hours and minutes together, what I want to do is I want to convert just everything into minutes to keep it consistent. Because notice that we were given your standard deviation in terms of 4 minutes. So if you put in like that's technically 2.25 because 15 minutes is a fourth of 60. So 2.25, we would then have to put 4 minutes in terms of hours because we just put this in as terms of hours. We need to get our units of measurement consistent. So I'm going to turn everything into minutes, which means I'm going to multiply 2 by 60, which gives me 120. So 2 hours, 15 minutes. That's 120 plus 15. So 120 is your 2 hours, and then your 15 minutes. So that's 135 minutes. Standard deviation is 4. Now everything is in the same unit of measurement, minutes, minutes. So then now my X value that I can put in here, 2 hours and 20 minutes is 120 plus 20, so 140 minutes. So I want to be at 140 minutes or more. So I'm going to put a ton of 9s in here. My standard my mean is 135. My standard deviation is 4, and then I go ahead and calculate. So the probability is 0.106 or 10.6%, close to 11% chance that it'll take longer than 2 hours and 20 minutes. Okay, I want you to go ahead and try doing B on your own. B is pretty much a repeat of this, slight change, different numbers, and then also we're told shorter than 2 hours and 20 minutes, which means 2 hours and 10 minutes, which means that we want to plug in 230 minutes into our calculator. So our lower bound, because we want to be less than 230, it's going to be between 0 and 230. Again, 135 and then 4. Oh, sorry, 130. That's why. Okay, so calculating that, we have, again, 0.106. So maybe you got to this point and you were like, wait a minute, that's the exact same probability. And I hope that you took a second and looked at these numbers. 140 minutes and 130 minutes. Compare them to the mean. They are both 5 minutes on either side, which is not quite our standard deviation, but close. And it's that same idea on the bell curve, where if we have an average of 135, and then we talk about, hey, here's 130, and here's 140, not my best diagram, but you get what I'm saying, that if we're talking about less than 130, we're talking about the area like this, versus greater than 140, we're talking about an area that looks like this. And since we're equal distances apart and we know that the normal distribution is symmetric about that mean, that area must be the same. So that's why, is that because they are an equal distance away from the mean, which means that the probability of less than and the probability of more than should be the same.